Well, according to the original schedule, I've already spoken 10 minutes overtime, so I will speak rather rapidly if you do not mind. First place, actually, according to history, my history is a bit schizophrenic. My contributions, I think, to NMR come in two quite different periods. One was in the period when I was working with Ramsey at Columbia, which was the very beginning of the molecular beam magnetic resonance. And then the second one is after I came to Harvard in 1947, so that my historical order referred to by Herman is a little bit schizophrenic. Well, now in particular, Henry spoke of the fact that after this discussion between Ramsey and Horner, that on a Monday, two groups were started separately doing experiments with oscillatory fields at Columbia. Well, I was in one of the two groups. Actually, the two groups, they were expected to finish in different orders, although we started at exactly the same time. One was the group of Ramsey, their overlapping membership in the group, Ramsey, Zacharias, Millman, and Cush, which was expected to get the first resonance because they were working with lithium chloride, which is easy to detect, and we were going to do the work with molecular hydrogen, which is much harder to detect and would take longer. On the other hand, should be much more interesting, since it was hydrogen and deuterium were particularly fundamental. Well, indeed, the group of working with lithium chloride indeed got a resonance, the well-known one, which has been shown by Henry, and shortly thereafter we got our first resonances, but were terribly disappointed. We expected to get a nice sharp curve such as that one, and what we got was an awful mess. It was something spread way out, looked like noise. It did seem to be coupled with the sample, but it was really pretty terrible, and I must admit very disappointing. In fact, we were so disappointed there are no copies of the original curves that I could find anywhere. I mean, they got sort of thrown out as useless data, the first exploration. This is what we expected to get. It's not what we found. But then we discovered if we worked with HD, the molecule consisting of one atom of hydrogen, one atom of deuterium, then we got two nice sharp resonances. We could measure the magnetic moment of the proton and the magnetic moment of the deuteron, which is what we set out to do. And in fact, we realized we could do even better by making the magnetic field a little bit longer, going from 5 centimeters to 15 centimeters. And so we decided that was the important thing to do, and that we would split up at that period. Ramsey already was to be a visiting professor at Stanford over the summer, and so Kellogg and Zacharias were going to make a list to prepare the parts for making the apparatus longer. Now, at that time, Columbia had the rule that a PhD could have only one author in the paper, and you have to submit some 1,000 copies of the paper, which means you had to wait till the physical review article came out. And so there was always the problem of inventing an uninteresting topic when there was a joint experiment, an uninteresting topic you could assign to the PhD student for him to write it. Well, I was the one, the PhD student, and it was decided to look at this mess that we had in H2 and some confusing things in D2 should be my PhD thesis, while the others prepared the improved apparatus for the magnetic moment measurement, and while Ramsey was in Stanford. Well, I began looking at it, and this resonance got a little more sensible if you decrease the current in the oscillatory field. We were terribly overpowering it, and after I think cutting it down by a factor of about 10, I got the following curve, which at least looked as if it might beginning to be something maybe different even from what we expected, but at least more spread out. Then I kept on. Unfortunately, I only did it by factors of 2. I should have done it by factors of 10, and it would have gone faster. But gradually improved things and went down to a very much lower current, and suddenly it became apparent that it wasn't just an utter mess. It was actually structure in the curve, and actually we were seeing what looked like 5 peaks, but this one, if it could be, perhaps was overlapping, would be split. And well, later on, after this improved apparatus was developed, then this curve went up to this form, which is very clearly a spectrum. And in fact, this is the first case in a magnetic resonance experiment of cheming multiple lines in the experiments. And we eventually understood this as due to the phenomena which we should have anticipated, but you never anticipate things the right things. We thought of the molecule as just holding the nuclei there, and the interactions within the molecule should be totally negligible, and therefore there should be no structure, whereas in fact the magnetic field of one proton at the position of the other proton was quite significant, would give rise to shift, and in fact it was quite clear what this was really a form of radio frequency spectroscopy that we were doing, and that we could get this in the case of H2 and could even understand what it was there. But then the other part that was also to have been my PhD thesis was to understand sort of peculiarities we had in the case of D2. It looked a little bit better. There again, it was a very much wider spread out spectrum than we expected. But again, as I found as I decreased the amplitude of the oscillatory field, it began to come out, following became fairly clear that we had a peak at about the right position, looking maybe as you want, but over here was this persistent background that would simply not go away. And then now we by that time understood, we're beginning to understand very crudely at the time of this, what this magnetic interaction was in the case of hydrogen. In the case of deuterium, it should have been much less, because the magnetic moment of the deuteron is much less than that of the hydrogen. The molecule is heavier, so it rotates more slowly, so the magnetic fields of rotation should be lower. So it should be a much narrower thing. In fact, if we take the results that would account for H2 well and predict what the spectrum should have looked like, it should have looked like these dashed lines down at the bottom. Instead, we got this long spread. Well, this clearly corresponded to something much more there, and it did begin to fit what you might expect from an electric quadrupole moment of the deuteron. And well, at this point it became apparent this was not the uninteresting problem for the PhD student to have for his thesis. So by mutual agreement, we decided we'd make these two problems together a joint one and go to the new apparatus, which when we did, we got this really very clear spectrum in this form, and corresponded indeed to there being a deuteron electric quadrupole moment, and which in turn implied the existence of a previously unsuspected nuclear tensor force. Well, I consider myself really incredibly lucky to thereby this process first to have written the first PhD thesis using magnetic resonance, to have observed the first multiple line structure in magnetic resonance, and to be shared in the discovery of the deuteron quadrupole moment. Well, that's the first phase of my work. Now, it doesn't directly maybe contribute to NMR, but it is the background out of which NMR came. Now, my next phase began in 1947 when I came to Harvard and was first debating what should I work on. Now, clearly, NMR had by then been invented as opposed to the molecular beam, the nuclear magnetic resonance, where we observe the effects by the change on the molecule or the atom rather than seeing the effect upon the radiation inducing the transitions. And that clearly had, the NMR technique clearly had some great advantages. First place, the apparatus was much simpler. Secondly, the resonances were much simpler because of collision narrowing. The fact that you have many collisions of the molecules, in that case, if you're doing with a gas at least, average many of the interactions out, such as the ones we observed in H2 and D2. These were averaged out by collisions. Now, this was a great advantage in some points of view. On the other hand, it was also a disadvantage from other points of view, and particularly I had been interested in studying those interactions. So actually, when I came to Harvard, I decided I would continue with the molecular beam aspect of it, looking at the isolated molecules, because I was particularly interested in the interactions, because it gave nuclear information and it gave molecular information. And that's in fact what all of my PhD students worked on here. not all of my, I did some of the high energy physics, but all the ones that did work on magnetic resonance really worked on it on molecular beam. And as a result, although I'd love to talk about the beautiful experiments they did, it's irrelevant to the present discussion. They were not done by NMR techniques, so I will skip that. However, the field of molecular beam magnetic resonance and NMR were sufficiently interrelated that on the theory of it, there was a lot of overlap. And as a result, I got involved in several theoretical, I'm primarily an experimentalist, involved in several theoretical things which were which were very relevant both to NMR and to molecular beams. One of these was on nuclear magnetic shielding and NMR chemical shifts. Now, my interest started from just nuclear magnetic shielding. In particular, it was one thing was a little disappointing. We could obviously do these beautiful experiments with molecular hydrogen, well, with molecules, and see these internal interactions. We could also measure the magnetic moments with great accuracy. But on the other hand, there's a problem, namely, we put on an external magnetic field, measure the precession frequency of the nucleus in that magnetic field, the net magnetic field. But the net magnetic field was the combination of the externally applied magnetic field and whatever internal field might result from the induced circulation of the electrons. This would essentially provide a shielding of the nucleus so that you could do a beautiful precise measurement of the frequency of the resonance. You could do a beautifully precise measurement of what the magnetic field was you put on, but the magnetic field at the nucleus was slightly different. And this was the magnetic shielding. Now, we'd known of this problem, and in fact, Willis Lamb in 1940, well, we don't have the date here, that makes a difference, but somewhere in the about 1942, actually published a paper for atoms. Now, in the case of atoms, it's very easy to calculate this. Namely, it's a central symmetry. You put on the external magnetic field, and the electrons just go circulating around a little bit more with the induced diamagnetism. You can calculate exactly what the effect was. On the other hand, for molecules, this is not so good because there are two centers of force, and particularly for H2 and D2 molecules like that, it was terrible because you have two equal centers of force. You don't know which one is going to go circulating around. In fact, it obviously isn't either of these. And this was the problem I wanted to tackle so we could really get benefit from this, to calculate something about what the shielding effect was. You couldn't determine it experimentally since it was proportional. The shielding effect was proportional to the magnetic field. But then Van Vleck has very correctly been mentioned by almost everyone so far. I also was a great admirer of his book on electric and magnetic susceptibilities and the work he had done on magnetic susceptibilities. And in particular, he had worried about the magnetic susceptibility of molecules. And I realized that I could take some of the ideas he had involved in that and calculate what the magnetic shielding should be in the case of molecules. And indeed, it's a rather awkward looking expression. This is sometimes called a high frequency terms here. This, however, could be, if it looks pretty awkward, you could make some evaluation. I'm not trying to define what the units are. Look at the paper that's reference gives. You really want to know that, and many people do. But you can also approximate this one by using closure and get a value of the magnetic shielding. And this still remains the fundamental theory of the magnetic shielding. Obviously, it also goes with chemical. It was clear it would go different with different molecules, giving rise to chemical shifts between different molecules. And although this is remains the fundamental theory, there have been vast improvements in the techniques of calculation. A number of great ingenuity has gone into calculating this and is used quite extensively. Then a second thing I did, I realized, although I did this original thing for the thing that was relevant both for atoms both for our molecules in the zeroth rotational state, as it was in the case of HD, and also as it was relevant to NMR, where you had these collision averaging of effect and averaged over all orientations. And but then I also realized that if you, in our case of individual molecules, there was an orientation dependence. We could tell what the orientation was. And in case of crystals, the same thing was true. So I actually modified the theory to include the orientation dependence, in which case the magnetic shielding constant sigma becomes a tensor of the second rank and could be used. Well, now, about the same period of time which this work was being done, I was sort of doing it on, I think I submitted this paper, first paper in 1949, about the same period of time, perhaps a little bit earlier. Experiments were coming up also showing the existence of chemical effects. I believe actually the first one really was Nico Bloembergen's, which is, again, in Physical Review 1949, is just an abstract of a meeting, which I believe he didn't show up for. I'm not sure about that. He can correct that. But nevertheless, it got published. That's when abstracts were published as part of the Physical Review. And then it also, a very early one was by Waller Knight on a metal shift, and then Dixon, Proctor, and Wu. And that has clearly become, although it started, from my point of view, my interest in this started with it being a nuisance. Namely, it was something that disturbed our measurements. It's clear one of the most important things of NMR has been the existence of the shifts, which provides the possibility of chemical identification. Well, this curve, the next thing I got involved in that one refers to the curve already shown, but in particular, Felix Bloch had been very interested in my theory of magnetic shielding, because he was interested in the chemical shift, and it was, in fact, one case he sort of called me his house theoretiker, which is sort of amusing since he's a theorist and I'm an experimentalist. But nevertheless, because I was doing some of the theory on his work, but then he came around to me with great glee and gave me a challenge. He pointed out that Arnold, Darmody, and Packard had studied ethyl alcohol, CH3, CH2OH, and found 3 resonances. Very nice, that's referred to. But the thing he really sort of put in the knife and twisted it, it said one of the characteristics of that theory was it was temperature independent, the first approximation. And he said this peak was temperature independent, this peak is temperature independent, and this peak shifts with temperature. Well, how do you explain that? Well, I didn't explain that. So I left the symbol CH3, CH2OH on my blackboard, so I stew about it for a while. A couple of days later, Erner Lirdell, who was the administrator for the ONR contract, you know, the person you just chiefly, I didn't even know he was a scientist up to that time. He was a great administrator. He did a marvelous job in the nuclear physics branch of ONR, came to my office, saw this symbol written on the backboard, and immediately for ethyl alcohol, and he said, what are you doing? Are you drinking it or are you studying it? I said, I'm studying it. And he said, oh, my PhD thesis was on that molecule, and I was able to show him my PhD thesis that the molecule was in a liquid form was associated, and the association came from the OHs going together. Well, as soon as he said that, the answer was clear, that the magnetic, quite reasonably, the magnetic shielding was different in the associated form and the non-associated form, since the nature, the surroundings were different, and as the function of temperature, the degree of association would vary, and that's exactly what it is. So it's the fastest paper I think I've ever wrote from conception on up. Erner Lirdell visited me about 10:30 in the morning. We had this brief conversation. We realized we had an explanation. We sat down, we wrote, we got a secretary to type, and before he left for Washington with a train at 2:30, we'd mailed off to the Journal of Chemical Physics a paper. What? Did you go out for a drink? We never got a chance to drink it. Well, now, somewhat similar, well, not quite as excitingly short, came up with an involvement of different form I've got on electron coupled spin-spin interactions. And this was, first place arose from experimental papers. Namely, there were 2 papers that came out quite early, one of Gutowski, McCall, Slichter, and McNeil. and the other of Hahn and Maxwell, both of whom have representatives here at the meeting. What they had discovered was that although in NMR you normally expect you don't get these internal interactions, that's one of the, because of the molecular collisions and collision narrowing, in the case of several different molecules, long complicated names I don't remember, there was an interaction in the form proportional to the interaction between the two spin, a spin-spin interaction proportional to I1 dot I2, the scalar product between those two. And it was fairly large, about 1 hertz in terms of frequency. And now, in one sense, that wasn't surprising me. I've worked we had a lot of these interactions, much bigger than that in our molecule. But on the other hand, the interactions that we were observing in our molecular beam experiments on the average averaged out to 0, so they shouldn't have been there at all. Secondly, for the spacing between the two different nuclei, even if they hadn't averaged out to 0, it shouldn't have been that big. So Ed Purcell and I sort of stewed upon this, worrying about other interactions, and we realized, yes, there is another interaction, which we called electron-coupled spin-spin interaction. Namely, well, if you think about it, simplest in the case, because that's one of the ones we worked out, HD, that's a singlet sigma molecule. The electron spins always are antiparallel. Well, therefore, if the nucleus A can interact with the electron near it, the other electron is going to be the opposite orientation. It can interact down there. Namely, through exchange coupling, you get a much more strong effect in distance. And we realized this could probably be something to test it. Our theory, we did the calculation in the case of HD, which is an easy molecule to calculate, found of 70 hertz. I can say that's much too big, but that's all right. You'd expect in the smaller molecule it would be much bigger than it would in the other, so it seemed to be the right reasonable order of magnitude. And eventually, eventually two things occurred on that. Our chairman here and Carr and Purcell did an experiment, actually found 43 plus or minus 0.5 hertz in HD, which is the one we'd calculated, and then later this got improved. Our calculation was improved. I did a better calculation, and then particularly Das and his associates did a better one of 40. Then later this got improved. Our calculation was improved. I did a better calculation, and then particularly Das and his associates did a better one of 42.457, which agreed quite nicely in that case and provided the basic structure for the many other cases where you got this kind of interaction. Well, I think I was going to say, say just very briefly, I also got some interaction with this thing referred to already by Bob Pound on negative absolute temperatures. Actually, the origin of that was that Bob had found a lithium fluoride crystal, which had this marvelous, intriguing property, puzzling property at the time, that namely, if you put it in a strong magnetic field, it took about 15, 20 minutes to come up to full strength. On the other hand, if you removed it from it and quickly put it back, it immediately came back up to the full strength. And what the worry was, what's the property it was remembering? Well, after he invited sort of Ed and myself to stew with him a little bit over I think this whole work was done in one weekend after he's made the original discovery of his crystal. And we found indeed two things out of it. One is the thing on so-called audio frequency. We found we could do sort of a cross between a molecular beam and an NMR experiment, namely put the sample in a strong magnetic field, determine what its resonance was, pull it out, put it into a low magnetic field, subject it to an audio frequency field, put it back and see if you got your original resonance. I'm thinking there was never much follow-up after this experiment. I thought it might be a great future technique, but we didn't follow up, and neither did anyone else. And then the other thing was this negative absolute temperature, which particularly was written up in the paper by out of the same weekend of Purcell and Pound. And then actually it had a peculiar, that had two subsequent things. Several times I gave colloquia on that, mentioning at least that work, and had two interesting effects. One was when I gave Towns told me at a much later time that a colloquium I had given at Columbia on negative absolute temperatures and pointing out the fact that resistances are intrinsically negative and everything's intrinsically an amplifier. And that it's one of the things that's helped stimulate him to really get settled down and working on Maser. And the second thing is when I gave this similar colloquium at Oxford, when I was there as a Guggenheim Fellow, Sir Francis Simon, who's sort of the professor of thermodynamics, the British professor of thermodynamics, really set out to show I was totally wrong, that this wasn't a real temperature. And we had long arguments over several weeks. Eventually, instead of he talking me out of it, I talked him out of it, at which point he said, but you should have written it up. You should do the thermodynamics of it right up. So I wrote up a paper at his instigation on thermodynamics and statistical mechanics at negative absolute temperature, which was sort of a fun paper to write up. I wrote it on a train between Oxford and Cambridge. I had Zemansky's book on thermodynamics on one knee and had a paper on the other. And whenever, and all I did was make the corrections you had to allow for when the fact that negative temperatures could exist. And this went along very smoothly. But one shock came out of it, namely when I began doing the second law of thermodynamics. I'd always jokingly said to myself, I hope I never write a paper contrary to the second law of thermodynamics. And I suddenly found myself writing a paper contrary to one of the more popular statements of the second law of thermodynamics, so-called Kelvin-Planck form of the second law has to be modified when you take into account this principle of increasing entropy goes on just as well, one way or another. Well, so there are a number of interesting things. I could go into that one a little bit more in detail, but I think I'd like to save a little bit of time, and so I would like to terminate, and want to just terminate and merely say how much I think all of us in all fields of science are indebted to Purcell, Pound, and Torrey, and Bloch, Hansen, and Packard for really introducing this marvelous NMR technique, which we all benefit great from, and it's been great fun for me to be partially at least associated with this. Thank you.